was due, I think it was yesterday, really. Is that 9-5? Practice problems? Answer key was posted this morning. As we've been saying, we're holding up the posting of the answer keys to avoid the temptation of merely copying from them. How are we doing on these mass-to-mass problems? You can open yours on your Chromebook, see how you did, see what is up here, and ask questions. Take a look at what you have. Are you confused on these mass-to-mass calculations? What does the word stoichiometry mean? That's what we're doing now. Stoichiometry, what does it mean? It is really when you use a balanced chemical equation. You know something in the equation, and you're finding something else. So, for instance, if I know what mass of this I have, I could find out what mass of that I need. I could find out what mass of this I would make, or mass of this I would make, based on a mass of anything. Or if I know a mass of one of the products, I can find what masses of the reactants I would need to make that amount of product. Kind of an interesting question here, trying to show you why different fuels can produce different amounts of pollutants. Are there any questions on this first problem? Any parts that were confusing to you? How about our second problem? This is burning octane, which is one of the hydrocarbons in gasoline. Were there any issues on this problem? Have a look. If you're not sure where any of these numbers are coming from, now's a great time to ask. Here's why you want to ask. We're still doing mass-to-mass calculations today and tomorrow. So you'll want to know how to do these, because we're going to take these calculations one step further with a concept called limiting reactants. For instance, what is a limiting reactant problem? Well, in this equation right here, we're burning octane, oct for 8 carbons. When we put masses of reactants together, we don't always put them in what we consider to be mole equivalents, meaning we may not always want to react 2 moles of this with 25 moles of that. That is the ratio they join at. But remember, we're trying to get a reaction to occur. With that said, which of these two things do you think is more expensive, especially right now? Which of these is the more expensive reactant? Yes. The octane is, especially right now. Why, especially right now? Why are gas prices shooting through the roof today, yesterday? Yes. There was a pipeline that was hacked. That was one of the major modes of transporting petroleum across our country. It was hacked and shut down, so now petroleum is not getting to the places it needs to be. That drives the prices up. This is by far more expensive than oxygen, because oxygen is found where? Yeah, it's in the air. So if I'm going to react these two, and I want to make sure all of this is reacting, that all of this can find the oxygen, I might want to put oxygen in a greater quantity than I would need, so that all the octane molecules can find oxygen molecules in order to combust. I would put in plentiful amounts. That's called in excess. I want the cheaper reactant to be available in excess so that the other reactant can find its partner. The excess reactant, when the reaction is over, where will it be? If we have excess oxygen, where's the oxygen going to be when the reaction's over? Just sitting there, unreacted. But it's not a problem in a chemical reaction if that excess reactant is wasted. It's okay if it's not expensive. Especially it's okay if it's not toxic or a pollutant of some kind. The reactant that is not available in extra amounts is called the limiting reactant. So if I had lots of oxygen and I didn't have as much of this to react with all the oxygen, the octane would be the limiting reactant. They call it limiting reactant is because the limiting reactant's the one that gets used up. And it will limit the amount of product that we can actually make. All right, no questions on this one. How about, did you get that octane was more of a problem in this particular problem, causing more carbon dioxide, one of the greenhouse gases? Everybody good there? And then our final problem, our final mass-to-mass practice problem before we move on to using mass-to-mass. Limiting reactants just uses the concept of mass-to-mass. How are we on this problem? Check over your work, you compare it. Now's the time to ask. If you have how would you say it in your country? Difficult. Was there any parts here that didn't match your work? Will there be a mass-to-mass problem on our exam? Absolutely. There'll actually be two mass-to-mass problems, and it'll be the type we're learning today, limiting reactants. So the kind of problem we're going to have today that we're going to learn to do, they will tell you an amount of one of the reactants that we're going to use. And then they'll tell you amount of the other reactant that's going to be used in the reaction. And then they're going to ask you how much product, one of the products you can make based on the mass of these two. It's not hard to do. If they give you the mass of carbon, could we figure out how much of the silicon carbide you could make? Yes. If they give you the mass of this, silicon dioxide, could you figure out how much of the silicon carbide you could make? Yes. Whichever one makes the lesser amount is the limiting reactant. Now, you may not understand what we're talking about. You're like, what do you mean? Well, let's say that we're going to make pizza the week of exams in here. Like the week before exams, we're going to make pizza, have a pizza party, and study chemistry. And you show up to class, and we've got the burners lit in the back of the room. And we've got like little things to put the pizza on. We're going to cook the pizzas with burners. That'll take a while. That's fine. We want a while for the pizzas to cook. That will give us more study time. But you come in for the study session. And in the back, we see 3 pizza crusts sitting on the table. Let's assume that we need a can of pizza sauce for every pizza we're going to make. For every pizza we're going to make, we're going to need 1 can of pizza sauce. And we have 5 cans. Then sitting on the table, there are bags of pepperoni. And let's say for every pizza, we need 1 bag of pepperoni. For every pizza, we're making pepperoni pizzas only. You're like, I don't want pepperoni on my pizza. Then take it off. This is a bag of pepperoni. This is a bag of pepperoni. Then we have bags of cheese. Then we have bags. That's the wrong color for cheese, I think. Then we have bags of cheese. There's a bag of cheese. For every pizza, we need a bag. One bag of cheese. Here's a bag of cheese. Every pizza, we need a bag of cheese. Question, how many pizzas can we make? Outstanding. We can really only make 2 pizzas. If we're making all pepperoni pizzas. Why can we only make 2? We only have 2 bags of pepperoni. That's the idea of limiting reactants. Whichever ingredient we need that can make the fewest is the one that limits it. Which one is our excess ingredients? Cheese is really the most excess of all of them because we only need how many bags of cheese? 2. So how many bags will we have left over? Is that 6 bags? Will we have a crust left over? Yes. Yes, we would. That's the idea of limiting reactants. For more on limiting reactants, today we have the 9-6 videos to watch, which will actually take this concept and apply it to mass-to-mass calculations. Tomorrow we'll have some practice problems. I believe it's 9-7. Good luck.